Lesson 15.2, Task 3. Evaluate trig functions given a point. The three basic trig functions can be defined using the coordinates x and y for any point on a circle centered at the origin with radius r. Alright, so in the previous two tasks, we were looking at the unit circle, which means it had a radius of 1. Now we're going to look at any circle with radius r. So r can be of different lengths now, but we're still going to do basically the same kind of thing. So we're still going to have an x and a y, which means we're still going to have cosine of x and sine of y. So we can still use these trig functions here as sine of theta is going to be y over r. Remember, sine is opposite over hypotenuse. So y over r, this would be my y over r, opposite over hypotenuse, because this is my theta here. And the cosine is adjacent over hypotenuse. So adjacent over hypotenuse. And then my tangent is going to be opposite over adjacent. So tangent is going to be opposite over adjacent, which is y divided by x. And so you can see they're just using these different variables in order to do that. And then it also states that x cannot be equal to 0. Remember, when you divide, you cannot divide by 0. So that means this x coordinate cannot be equal to 0. Plus, if that were a distance of 0, there wouldn't be a triangle here anyways. So there's kind of a couple reasons why that makes sense. All right, so using coordinates on the unit circle, you can determine that the sine and cosine functions can be defined for any angle theta. However, the tangent function is not defined when x equals 0. Again, you can't divide by 0. This occurs when theta equals negative pi over 2, 3 pi over 2, and then it goes on ... to 2n plus 1 pi over 2, where n is all integers. Because the values of sine and cosine functions are coordinates of points on the unit circle, the output for the sine and cosine functions will always range from negative 1 to 1. Again, unit circle is going to go from negative 1 to 1. The output of the tangent function, however, can be arbitrarily large, positive or negative, because the denominator can become arbitrarily small as long as it does not equal 0. All right, so here's a little chart that will help you with the domain and range. So when we start graphing these, you'll see that we have kind of a different graph for trig functions that have angles on it instead of just numbers. So your domain is going to be angles such that your angles are all real numbers. And then it's going to be cosine will be all reals as well. All right, and then your tangent, of course, is limited to integers. Z represents integers here. And remember, it can't equal 0. So your range is going to fall between negative 1 and 1. So the sine of theta will fall between negative 1 and 1. And the cosine will also fall between negative 1 and 1. And then the tangent will be all real numbers. So given a point on the terminal side of an angle of rotation, you can use the definitions above to evaluate the sine, cosine, and tangent ratios of any angle on the three corresponding trig functions. Find the value of sine, cosine, and tangent of theta. All right, so if we wanted to find the trig values using this ordered pair here, we'd have to find what the radius is. So if we know that this is negative 3 and this is 4, okay, 3, 4, 5, hopefully you know this is a 3, 4, 5 triangle. That's one of your special right triangles that you see a lot on the ACT. But just because it's in quadrant 2 makes your x negative, but it still kind of works the same thing. So again, this is going to be your Pythagorean triple, 3, 4, 5. So that's going to have this side length will be negative 3, this one will be 4, and your radius would be 5 units. All right, so you could easily find opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent using that information. So it says, is the angle on the domain of all three functions? is the angle on the domain of all three functions. And I'm going to say yes, because it doesn't fall on this axis, so it should be for all three. So it says yes, sine of theta and cosine of theta have a domain of all real numbers. The angle's terminal side is not along the y-axis, so tangent is also all real numbers. So yes, again, the domain is all real numbers for each of the three trig functions. Find the value of r. All right, I kind of spoiled this. I told you it was a 3, 4, 5 triangle. You can use Pythagorean Theorem in order to find that. So if you look here, you know that a squared plus b squared equals c squared. Well, in this case, we use x squared plus y squared equals r squared, just to fit to the variables that we're using for the triangle. But it's still the same thing. A squared plus b squared equals c squared. And to find c, you take the square root of both sides. So in this case, they took the square root of both sides. All right, so the value of r is 5. And then it says, what theorem can you use? Again, that is Pythagorean Theorem. Let's see, Pythago. Always have to think about that spelling there. All right. So Pythagorean Theorem is what we use to do that. And then we're going to substitute. Substitute the values of x, y, and r into the definition. Okay, so just like what I was saying before. Okay, so sine is opposite over hypotenuse. So according to our triangle up there, it's y over r, which is 4 over 5. Cosine is 3 over 5, and tangent is negative 4 over 3. All right, explain how you can determine the sign of the value for each function before substitution. All right, if either x and y are negative, both are negative, determine the quadrant and use the sign chart. Okay, that's what we want to do. So you want to figure out which quadrant it's in and then determine the sign chart from there. All right, and that is the only one that makes sense. So we're going to go with that one. All right, so that's a little bit more about your trig functions. So that is all for task 3. If you have any questions, let me know. Lesson 15.2, task 4. Use trigonometric functions to solve a real-world problem. You can use trig functions to solve real-world problems involving right triangles or circular rotation. An airplane on a final approach descends at an angle of negative 3% or 3 degrees to the horizon. What is its change in elevation after it flies 6,000 feet horizontally towards the runway, when the plane is at an elevation of 3,200 feet on its final approach? At what horizontal distance from the runway is it? All right, so it gives us a picture here, and it shows us that this distance here is 6,000, and we're looking for this unknown distance here. And this is negative 3 degrees. So we're going to sketch a graph with the plane as the original at the origin to find the change in elevation over 6,000 horizontal feet. The horizontal distance traveled is the x-coordinate and the change in elevation is the y-coordinate. Use the angle of descent and the horizontal distance to find the change in elevation. All right. All right, so we're given the elevation in feet, and here is the plane's initial position, and we were given this distance here, I believe. This is our unknown, and it says the plane's position after traveling 6,000 feet horizontally. All right, so what are we going to use? So it looks like we are using the tangent function. That means we are either given or using the opposite and the adjacent. All right, so the opposite is the unknown, and the adjacent is, in this case, the x, the 6,000 feet. All right, so what is tan of negative 3 degrees equals y over 6,000? So you have to think back to geometry or integrated math 2. And when you look at these on your calculator, make sure that you plug this in and you go to mode, and you have to go to degree measure. Because we're given this in degree, if you don't have this in degree, you're not going to get this answer. So I checked it just a minute ago. It does work, so click on degree if it's not in degree. And then when you go to calculate, you can just type this in as 6,000 times tan of -3. Now, we started out with this equation because we know that tan is opposite over adjacent. So we just plugged in the information. But to solve for y, you have to multiply both sides by 6,000. So if we go 6,000 times tangent of -3, again, as long as you have it in degree mode, it should give you this answer here. So it says, why is the tangent function used instead of sine or cosine? All right, so we use the tangent because the adjacent and the opposite are the ones that we either have or are looking for. So the tangent is the best use, or the best one to use with the given information. What mode of angle measure should you use for your calculator? Okay, I just mentioned that, so you are going to go to mode and make sure this is in degree mode. So it has to be in degree mode or you'll get a different answer. You'll get an answer, but it will not be correct because it won't be in degrees. All right, so over 6,000 horizontal feet, the plane's elevation decreases about 314 feet. The elevation change will be -3,200 feet when the plane reaches the runway. Use this fact in the angle of descent to find the horizontal distance. Okay, if you remember in the very beginning, we read that the plane is at an elevation of 3,200 feet on its final approach. So when it reaches the runway, we know that it's going to have descended -3,200 feet. All right, so we can use that fact and plug that in here as well. All right, so now we're going to have tan of -3 degrees equals -3,200 over x. Now, to solve for x, we have to multiply by the denominator. So multiply both sides by x, and then to get x by itself, divide by tan of -3 degrees. So they rearranged that, they skipped a step, but that's how you get to this point. Again, this is review from geometry, I guess, so maybe it's been a minute since you've done it. All right, again, you can take your calculator and you can plug this in and see we're still in degree mode. So I'm going to type in -3,200 and divide that by tan of -3. And you see how I put this whole thing in parentheses as well, not just the -3, because I want to make sure that my calculator does this in the correct order. So I get 61,059.6374, which is roughly 61,060. So as long as you have it in the right mode and you type it in correctly, you should get that answer. And then it says, why is the unknown in the denominator? Well, the unknown is going to be whatever part that you're searching for, so whatever's not given. So you have to plug in the information given, and then sometimes it'll be the denominator, sometimes it would be the numerator. So in this case, we're looking for the denominator because that was the unknown. All right, so when the plane is at an elevation of 3,200 feet, it will be at a horizontal distance of about 61,060 feet, or about 11.6 miles from the runway. So what they've done is convert feet to miles to figure out how far it is from the runway. All right, that's all for task 4. If you have any questions, let me know.